What does that mean about the equilibrium constant for your strong acids and bases? K was really, really big. What does that mean as far as an individual reaction goes? Well, let's pick HA. And in this case, we're going to say HA is a strong acid. When we add it to water, what happens? Yes, it dissolves, but it goes even further than that. It forms, if we're going to have it react with the water, forms our hydronium or our H+, depending on your perspective, and our conjugate base. When we add one molecule of HA to water, how much hydronium do we get? 1. How do we know it's 1? What's that? Okay, I don't think I heard anybody, so I'm just going to pretend I did. Because it completely ionizes, right? So it completely dissociates into those ions. So if we start with 1, that reaction, as far as we're concerned, is 100% complete, completely makes hydrogen ion. So if we wanted to push to the next thing, if we looked back at our definitions, one of our definitions was looking at something known as the pH, which was just a way of trying to rank hydrogen ion concentration, or ultimately a way of looking at some form of danger of that solution quickly and easily. So if we go through and look at a strong acid, it completely ionizes. We can solve for the hydrogen ion concentration immediately and immediately turn that into a pH. Very swift. We don't have to worry about any equilibriums because our equilibrium constant is so massive. We don't have to worry about some of that hydrogen ion disappearing. What happens when we shift to a weak acid or base? Not quite doesn't, but it's an incomplete dissociation. What does that mean about our equilibrium constant? K is usually less than 1. Depending on how much less than 1, we'd have to evaluate different things. What does that mean to us as far as drawing out the reaction? If we now take our weak acid and we add it to water, what happens? Going to get to that in a second. We form H3O plus and A minus. But you brought up an interesting point. It's at equilibrium, which means not only do I dissociate, I also go back the other direction. Which means when we look at a weak acid and we're trying to determine its pH, the concentration of hydrogen ion, we can't immediately just say that the concentration of hydrogen ion is the same as what we started with. Okay? If we start with 1 molecule of HA, or sorry, we can't do that. Let's do 1 mole of HA. Instead of generating 1 mole of hydrogen ion, we generate some number less than that. How much less than that is dependent on the equilibrium constant. Okay? So we would have to go through and in this case solve some kind of an ice chart to apply that, so that we could then determine what this concentration was, so we can warn all the little kids not to stick their fingers in it. Okay? Don't put it in the squirt gun. Okay? Kind of makes sense? So those applications should have been very, very similar to what you saw in chapter 14. Very direct, very straightforward. We don't have to worry too much about it. Okay? What we then did in chapter 16 is now we made it a little bit more difficult. Okay? We'll go simple first. Now we brought up this idea of buffers. Okay? What a buffer is doing is stabilizing the pH. Okay? Which means if I add acid, the pH doesn't change. If I add base, pH still doesn't change. Okay? So what has to be present if I add acid and the pH doesn't change? What has to be in the solution? A base. What happens if I add base and the pH doesn't change? What also has to be in the solution? Acid. Okay? So what we have to have is some solution that has both an acid and a base present. The problem is if we go back to now strong acids and bases, what's the issue? If I add a strong acid with a strong base, neither of them go into equilibrium. They both react with each other, neutralize, and now I have one solution that has one or the other, or neither, in which case I don't have a buffer. Okay? So how can we make a buffer with an acid and a base? What has to be characteristically true for this to be a buffer? They must be weak. As long as they are weak, when I add an acid, the weak base reacts with it, neutralizes it. We don't see a change in the pH. When I add a base, that will react with the weak acid, again, neutralizing that effect, and we don't see a change in the pH. So a buffer is just the situation where we have a weak acid and a weak base. Do they have to be the conjugates of each other? That one's a trickier question. No. Why do we pick problems such that they are conjugates of each other? It makes it a lot easier. So if you're going to move into biochemistry, you typically deal with buffer solutions that contain only one type of conjugate partners. If we mix in other conjugate acids and bases, we now have to deal with two different equilibriums. Two different equilibriums being solved in the same solution requires a lot of effort and work on our part. So we typically don't see those situations. Okay? But it still does work. Okay? So what happens to make these? So we said we need a weak acid and a weak base. So let's look at a couple cases where we're going to attempt to make a buffer. I'm going to take a weak acid and I'm going to add a strong base. Okay? For it to be a buffer, I have to have weak acid and weak base. Do I have that? Do I have that immediately? Let's start with that. No. Okay? I'm not saying anything about the amounts of these species, though. So if we mix these two things, is it possible that we could mix them in the perfect ratio such that we generate a weak acid and a weak base? Okay, well, let's go through and establish that. Let's say I start with 4 weak acids and I add 2 strong bases. Okay? When we put these two together, the first thing we're going to have to evaluate is what's going on with that strong base. Okay? The biggest issues that we learned from the first chapter, was it 15, was that strong bases don't reach equilibrium. So what we have to do is go through a non-equilibrium system. What happens when I add that weak acid and the strong base to each other? What do bases react with? Acids. Do we have an acid and a base? Yes. So what happens? They react. Which one's the limiting reactant? The strong base. So what happens? We react all of the strong base. And at the end of that reaction, what do I end up with? I now have 2 of the weak acid because the strong base killed 2 of them. How much of the strong base do I have left? Should have none. Why none? Because 2 reacted. Where did that weak acid go? Because we can't create or destroy matter. So if we run this reaction, if we run any reaction, we're going to have reactants and products. What's the product of mixing a base with an acid? Conjugates. Our strong base completely dissociates into its useless counterion. Our weak acid now is lost to hydrogen and becomes a weak base. We started with how much of that weak base? 0. In the course of the reaction, the strong base reacted with our weak acid, and we lost that weak acid. What did it become? Strong base. Which means, in the course of the reaction, we increased our weak base by 2 units. At the end of that reaction, what do we have? We have a little bit of weak acid, we have a little bit of weak base, which means buffer. Okay? What we've just gone through and done here is a modified barn chart. Before the strong acid, addition of the strong acid, reaction, neutralization. Okay? Why is this so much easier to see than doing a barn chart? Typically when you go through and do a barn chart, what are the numbers that you're using? Are they nice whole numbers? No. They're usually goofy concentrations that are impossible to see or understand. It's still the same mathematics. You're still going through the same steps. You just can't do it in your head. Okay? Let's look at another possibility. Instead of a weak acid and a strong base, let's go through and add a strong acid. What happens when we mix an acid with a weak acid? A strong acid and a weak acid. We get a strong acid. Okay? No reaction occurs. The strong acid is going to generate 2 molecules of hydrogen or acid component. What happens with our weak acid? It's going to generate some hydrogen ion, but how much does it generate? Hard to tell. That's dependent on the equilibrium constant. So when we go through and do this reaction, what we end up with is just acid. Yes, we have a weak acid, but do we have the weak base? No. Do we have a buffer? No, because we don't have both the weak acid and the weak base. Okay? So when we go through individual problems, there were 2 types on your exams. One of them said something along the lines of we mix ammonia with ammonium. Okay? Most of the problems are going to come through and trying to come up with the equation. So if I mix ammonia with ammonium, nearly everybody that I graded came up with this balanced or attempted to balance reaction. I take ammonia and I mix it with ammonium, and then you drew an arrow and then there was a giant question mark. You had no idea what to draw after that. Okay? What you tried to do was jam all the information in one step. Breathe. Don't. Do it 1 step at a time. Okay? That doesn't work for you. So let's say, okay, I've got ammonia with, but no with, let's just look at ammonia. What happens when ammonia hits water? What is ammonia? Fair enough. Acid or a base? It's a base. What happens when it acts as a base? What does it need to do? Accept a hydrogen. Okay, if it accepts a hydrogen, what does it look like? What would our other product be? Okay. Is it a strong acid or strong base? It's not one of those ones we've memorized, so it's at equilibrium. Now that we've breathed, we can go ahead and read the rest of the question. We mixed it with ammonium. True, we've mixed it with ammonium. Do I have an equation that now shows a relationship between ammonia and ammonium? Yep. Do I need a new equation? No, it's already there. I've already got the problem. I can now go through and start to solve it. Just because the question tells you that you're mixing two things doesn't mean they're reactants necessarily. Okay? Write out your reaction and see what happens. It may turn out that they aren't being reacted with each other. Okay? One of the other big red flags with this one. Ammonia, is that a strong acid or base? Not strong, it's weak. It's a weak base. What about ammonium? It's a weak base. What do we have if we have 2 weeks? 14 days. We have a buffer solution. If we've got a buffer, we should go through and evaluate an ice chart and try and piece that together slowly. Okay? What happens if now we go through and we say we take ammonia with sodium hydroxide? We could go through and say, oh, well, hydroxide shows up on both sides of the equations. Okay? That's true, but what's special about sodium hydroxide? It's a strong base. What did we know from chapter 15 about strong anything? Completely ionizes, which means no equilibrium. This equation that we've got shown down here, where it shows hydroxide and ammonia, what does this arrow in between represent? Equilibrium. Is this equation valid? No. We must evaluate based off of our strong, which is not an equilibrium problem. We must completely ionize it and evaluate after that fact. If you have the presence of strong anything, go through and evaluate that process first and decide, is anything going to react with that strong? In this case, sodium hydroxide is a strong base. What needs to react with a strong base? Acid. Do we have any acid present?
Yes.
We mixed NH3 with sodium hydroxide. Do we have any acid present? No. If we let ammonia come to equilibrium, yes, we generate acid. What happens with that acid immediately? Completely reacts with the sodium hydroxide. We push the equilibrium back to the hydroxide. We don't have to worry about it. Okay? We only have to evaluate the strong base. Okay? Questions about that? It'll be easy, right? Okay. Work it slowly. I promise you'll do okay. That's a bad promise. You'll do better. How about that? If you've got any questions, feel free to ask. I will go ahead and stop there for real now.